Welcome to the Cosmic Savannah with Dr. Daniel Kahneman
and Dr. Jacinta Delhaze. Each episode, we'll be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Welcome to episode 42.
Hi everyone, today we are going to be talking about something slightly different, astrogeology.
Yes, well, astrogeology, geology, petrology, and some astrobiology. So we are going to be talking to Dr. Eugene Grosch, and he is a geologist and petrologist. So he studies how the structures of rocks form and then how minerals and other elements interact in the Earth's crust. And ultimately, we get to the big question, which is how these processes can form the conditions where life can form.
Yes, all of the kind of big questions. It's very exciting. It's a little bit outside of our field, so I'm excited to learn a lot. But before we get into that, there's a very exciting event happening tonight, or on the night that we are recording this, which is the 30th of September.
Indeed. The NSTF South 32 Awards are happening tonight. And as we mentioned a few weeks ago on the podcast, the Cosmic Savannah was nominated in the Communications Award category. So the NSTF Awards are the National Science and Technology Forum Awards in South Africa, and they are considered the science Oscars in South Africa. They have various categories, communications just being one of them, but also for research and innovation, and all of the cutting edge scientists in the country are present. And the Cosmic Savannah was selected as a finalist.
Yeah, it's a fancy kind of gala dinner tonight to celebrate all of the finalists and to announce the winners. And it's kind of like the science Oscars of South Africa. Everyone gets dressed up. Unfortunately, I won't be there because I'm in Australia. So I'm very sad to miss that. But Dan, you are going to be there and you're going to be all dressed up because you are actually nominated not for one, but not for two, but for 3 awards.
Yeah, so I was also nominated for the Communications Award in my private capacity or personal capacity, not private work. But yes, so for some of the other work that I've done, the podcast being one of them, but then also things like the films and the visitor center, the 200-year celebrations. So I've been nominated in the Communications Award for that. And I've also been nominated in the Special Theme Award. So each year there's a special theme. And this year the theme is sustainable sort of development in the creative economy. In that category, I've been nominated again for the work of the planetarium films, the indigenous star law animations that I've been working on, and just the sort of stimulating the creative economy. It's very exciting, and I'm a little nervous today, I won't lie. A few butterflies in my stomach. Looking forward to getting dressed up in my tux. And
yeah, you got yourself a new tux for the occasion.
I did. And a new moon boot because I had an operation on my foot. So I'll be in a tux and a moon boot and crutches. But I'll try and pull it off with some glamour.
Yeah, you'll have to post some pictures on Instagram for us in your tux. And also, Dan, I would like to follow along because, as I said, I'm in Australia. I'll be trying to stay up until about 2 a.m. when the ceremony is on. But can you please be posting on Instagram stories so that I can follow along? Because I know you're not very comfortable Instagram stories, but I need to be able to see it from your perspective.
I will try my best. I'm not very comfortable at all. And with crutches on, it's hard to use your hand or your phone. But I will try my best. I'll promise at least one.
Yes, at least one. Great. Alrighty, so back to the topic at hand. Dan, you spoke with Eugene earlier in the week.
Yeah, so I got in touch with Eugene a few weeks ago on the podcast. We mentioned astrobiology and, this. With astronomy, we're always talking about how elements are formed and supernova and neutron star explosions, and then how they then are recycled into new stars and solar systems. But there's always kind of this missing link between that phase and then the sort of full Earth where life can form. So I was very interested in how that happened. And we spoke to Eugene, who is a geologist and petrologist. So he studies the rocks, sedimentary rocks, as well as metamorphic rocks, and then how minerals form. So he does a very good job of explaining it, much better than I can. He puts his lecturer hat on, and I learned a lot. I had a great conversation. I really enjoyed it.
Wonderful. Well, let's hear from Eugene.
So today we're joined by Dr. Eugene Grosch. He is a senior lecturer at Rhodes University in Makanda in South Africa. Eugene, welcome to the Cosmic Savannah.
Thank you, Daniel. It's a pleasure to be on your show. It's very exciting. So thanks.
Yeah, thanks for joining us. I think that, I'm very excited. This is something outside of my field. I tried to read your thesis abstract and I couldn't understand pretty much every second word. So,
Sorry about that.
so I think it's going to be quite interesting and hopefully interesting to our listeners too. Maybe to just get started, can you tell us a little bit about yourself, how you got into geology and petrology, and maybe what geology and petrology are?
Sure. Well, I was born in Cape Town and I grew up in Mitchell's Plain and Grassy Park. I always enjoyed reading and traveling and hiking outdoors and being in nature and sports. I've always had a curiosity about how things work in nature. And yeah, I sort of went to university and found this interesting subject called geology, where I could take all of my interests like chemistry and physics and apply it into geology. I completed an honors degree in geology at UCT. And then in 2003, I was lucky to be chosen to go to Antarctica to do geological fieldwork on the continent there and to map out and sample some of the mountain ranges, or what they called nunataks, on either side of the continent's second largest glacier. So this formed part of my master's degree that I completed in 2005. After this, I wanted to earn some salary and get a job. And so I went to work as an environmental geologist for a while, looking at contaminated land sites and environmental drilling projects. And then ultimately, I decided I wanted to come back into academia and do research. So I registered for a PhD degree. And luckily, my industry experience actually helped me because I was doing drilling in different projects in South Africa. And my PhD supervisor was looking for somebody to do scientific drilling into Africa's oldest rocks to retrieve fresh samples in the Barberton mountain land of Mpumalanga province in South Africa. And these rocks were 3.5 billion years old, and it hasn't been drilled before, so it was quite exciting project. And that formed the basis of my PhD research, which I finished in 2011. And I then did 4 years of postdoctoral research at the University of Bergen in Norway, using various analytical techniques to study these ancient rocks. And yeah, now I'm based at Rhodes University. I'm married to my wife, Nicola. I have a 4-year-old daughter called Emily, and she told me to tell you guys that the name of her preschool is called Shooting Stars. She thought the astronomers would like that.
I do like that. That's wonderful. So you've had a pretty varied career already. I mean, there's a lot to unpack. I think that Antarctica is immediately appealing, and studying the rocks down there. It's a largely kind of unexplored area of the world. And from my understanding of Antarctica is it was once more tropical or treed, or is that the sort of stuff you're looking at, or are you looking at the sort of original rocks there?
Yeah. No, I think Antarctica was once part of a major supercontinent called Gondwana that formed about 560 million years ago. And there were a range of climates on the single supercontinent. And there are sedimentary deposits there that can record different depositional environments. But I was more interested in, as you spoke about earlier, the bedrock, the ancient rocks, the old rocks that are the crystalline basement in the area, looking at the pressure and the temperature conditions under which these rocks formed in mountain belts and so forth. And also trying to understand the major structural discontinuity underneath this glacier by using modeling on these rocks.
And then when you are looking at, South Africa's oldest rocks in the Barberton region, what are you looking for there?
Oh, Barberton is very special because we find that they're the oldest rocks in Africa, and it's also very well known for gold deposits. Where there's a number of gold deposits around the town of Barberton, like the Sheba gold mine and the Agnes gold mine. And also, there are very few places in the world where you can study rocks of this age that help us to understand what we call the Archean period of Earth history. There's other places, maybe like in the Pilbara Craton of Western Australia, but there's very few places where we can do this. And Barberton is probably the best place to actually do it. It's interesting because in 1969, there was a new class of volcanic rock discovered in Barberton by Maurice Viljoen and Richard Viljoen. And they called this rock a komatiite, which is a very high temperature lava that erupted on the Earth's surface when the Earth was still very young. So Barberton is quite famous for these komatiites. And I'm busy studying them and mapping out these rocks in the field to look at the volcanic stratigraphy and to try and understand if the Earth was much hotter 3.5 billion years ago than it was today. Yeah, and also we find it's fascinating that Barberton, the rocks are exceptionally well preserved, and that gives us a unique window into studying geological and potential biological processes on the early Earth. For example, we don't really know if mountain building processes were operating at this time during the Archean. We're also trying to understand what types of rocks are preserved there. We had a paper in 2017 showing that there's a fragment of oceanic crust that's 3.3 billion years old preserved here in Barberton. And so we got some of the oldest fragments of continental crust. We're trying to understand what the Earth's atmosphere was like. What was the chemistry of the Earth's atmosphere? We now have an idea that we think that there's very little oxygen around in the Earth's atmosphere 3.4 billion years ago. I'm trying to understand surface environments. What was the surface conditions like on the Earth? And what is the interaction between seawater and rocks? And also, is there any potential surface or subsurface environments that could be habitable zones for early life? So there's a lot of research and a lot of questions that I'm trying to address. And the more I learn, the more I need to learn more,
That such as research, and I mean that's why we love it, right?
Yeah, exactly.
So the prospects of early life and learning about them from these Barberton rocks is very interesting, and I think we can get into that in a moment. But before we get there, another thing I wanted to talk to you a little bit about is from an astronomical perspective, and we've spoken about this many times on the podcast before. You mentioned gold in the rocks, and from an astronomical perspective, we know now, only as recently as 2017, that most of the gold in the universe is formed in neutron star mergers. So when two neutron stars merge and have this kilonova explosion, they create a lot of gold and other heavy elements which spread through the universe. And then we've also talked in some detail about the planetary formation process, so how stars form and these elements then get reincorporated into new stars, which then sort of recycle the elements, and around these stars planetary disks begin to form, and then ultimately planets. So from an astronomical perspective, we can kind of understand the formation of the elements and how they kind of get around in the universe. But what's unclear to me, and what I'd like to ask you, is how does that then form an Earth and get to the point where, as you mentioned, there's an ocean, and now we start looking at atmospheres and things. For me, there's a kind of gap in terms of how these rocks form, and the first a sort of molten planet, and so maybe you can talk a little bit about that if possible.
Yeah, that's quite a big question. Yeah. I can try and give an explanation of maybe 50 million years of solar system formation in 3 minutes, but I'll try and have a go, Daniel. We know that from meteorites, for studying meteorites and the age of meteorites, that there was a solar nebula or a cloud of solar nebula around 4.56 billion years ago. Okay, and that this nebula consisted mostly of molecular hydrogen, helium, minor beryllium, and lithium. And there were other heavier elements as well in minor proportions, as well as solid dust particles that was created by nuclear synthesis reactions in early nearby stars and supernova. So this nebula cloud began to collapse because of gravitational forces and interactions, and eventually it started to rotate and flatten into a disc-like shape as a result of centrifugal forces. The majority of the mass moved to the center of the solar disk, where we started to form an early sun. And eventually, the inner terrestrial planets started to form from smaller coalition of these dust particles and rocky materials. Eventually, these rocky materials formed several kilometer-sized bodies called planetesimals, and the gravitational collapse started to form these planets. Most of the elements and materials went into the center of this disk, and hydrogen started to fuse to form helium, and that's when we see the ignition of our early stars. The sun had a huge control on the formation of our planets and the composition, the chemical composition of our planets, because it generated a massive pressure temperature gradient as well as the solar wind. So all the volatile elements, the light elements, got blasted away by the solar wind at an early stage towards the outer, more cooler parts of the solar system. And the more inner planets like Mars and Venus, Mercury, with thinner atmospheres, they tended to accumulate the more heavier refractory elements like calcium oxide, titanium oxide, and so forth. So, depending on where you were in terms of your distance from the sun as a planet, your composition will be controlled by the distance from the sun. And also, the iron silica ratio of a planet is controlled by its distance from the sun. For example, the iron silica bulk composition of the Earth would be very different to that from Mars. And so we see, for example, now that when the solar system formed, we had rocky planets on the inner parts of our solar system, and then beyond the so-called snow line, where the condensation temperatures were lower, we got the gas giants like Jupiter, Saturn, and also Uranus. So that's basically like a sort of a model of how the early solar system formed. But the Earth itself, when it accreted, it was going through major phases of heavy bombardment by meteorites and comets. And so around 4.3 billion years ago, we had the Earth bombarded by heavy objects, asteroids, and so forth. Even the Earth collided with a massive object about 1/10 its size, and the fragments of this collision started to coalesce and form the moon that we know today. So the Earth started to cool down eventually. It was a hot body. It's gone through quite a complex process of differentiation after its accretion. It segregated out into layers that was controlled under density processes and chemical processes. For example, all the heavier elements like iron and nickel, they sunk down into the central part or the core of the Earth, and the lighter elements like silica and aluminium floated to the top. And today we know that the Earth is layered because of its cooling history, and we have layers on the Earth like the continental and oceanic crust, which makes up about 1 or 2% of the thickness of the Earth. And then we have these layers like the upper and the lower mantle. And then we have an inner liquid metal core that's convecting, and then we have a solid metal liquid core. And you have to drill down 2,900 kilometers to get to this liquid metal core in the Earth that's still convecting today and responsible for the Earth's magnetic field.
But nobody's ever done that, right?
Nobody's done that, but we know from seismic measurements, from P waves and from S waves. P waves are compressional waves, and S waves are shear waves. And we noticed that at a certain depth of around 2,900 kilometers, the shear waves disappear. That's because they can't travel through liquid. So we suspect there's a liquid metal core from geophysical studies that we're doing.
You can tell you're a lecturer, by the way. You're very good at explaining things. So just to explain to the listeners, P waves and S waves. So essentially what you're talking about is when an earthquake happens somewhere on the Earth, you can monitor how the waves travel, not just along the surface to another point, but also through the Earth.
Exactly.
And from that, you've got a probe sort of going directly through the Earth.
Yeah, that's a very good explanation. And you can have a seismic station on the other side of the Earth picking up the waves and measuring and looking for them. So that's a probe into the deep Earth. There's other ways as well. We do actually find rocks from deep down in the Earth's mantle, 300 kilometers deep. Here in South Africa, in kimberlite pipes, the magma brings these rocks up, and they contain diamonds. And South Africa is very famous for its beautiful diamonds that gets brought up from deep in the Earth's mantle, where we can study these rocks. So there are opportunities to get samples from about 300 kilometers down.
So there's a lot to unpack, and just while we're talking about diamonds and gold, and South Africa is kind of famous for our diamonds and gold, we're not still forming these kimberlite pipes, are we?
No, I mean the kimberlite pipes. There's two groups of kimberlite pipes. There's the group one kimberlite pipes, which is a basaltic composition, and a group two kimberlite pipes, and they were placed into the craton or the stable part of our continental crust at 120 million years ago and at 90 million years ago. These kimberlite pipes are much younger than the diamonds. We actually had a professor at UCT, Steve Richardson. He studied these diamonds, and the diamonds encapsulated little minerals like pyroxene, and he dated the minerals that were trapped inside diamonds, and like sulfides and pyroxenes, and he determined the age of the diamonds. The diamonds are 3.4 billion years old, 2.9 billion years old, but the kimberlite magma that brought them up to the Earth's surface is much younger than the diamonds. They are 90 million years old, for example, and this kimberlite magma acts as a transport mechanism to bring ancient diamonds up to the Earth's surface from great depths.
So basically, very deep in the Earth's crust, these diamonds are forming because carbon, I mean, which is what diamonds are made of, is cooling at the perfect conditions, density and temperature to create diamonds. So you're getting, I don't know, a seam or something of diamonds very, very deep down, and then those get broken up and transported up at a temperature which doesn't destroy the diamonds.
Yeah, I mean, there is a process. We find diamonds, for example, in what we call eclogites. These were ancient oceanic crusts that had organic sediments in them. So this ancient oceanic crust with organic material got subducted deep into the mantle by a process called subduction of oceanic crust. And the rocks, along with this organic material, gets forced under high pressures into the diamond stability field. And because organic carbon can't be stable down there in its amorphous form, you start to form diamond at these very, very high pressures. And like you said earlier, these rocks containing the diamonds are erupted quite quickly up to the Earth's surface to preserve the diamonds. So that's correct, yes.
Okay, so the carbon's actually coming from the surface.
Correct, yeah.
The diamonds are being created by organic material.
That's right. They've looked at the diamond compositions and the inclusions and the fluid inclusions, and they've looked at nitrogen isotopes, and they could match these isotopic signatures to surface carbon or surface organic material that was subducted deep into the Earth's mantle.
Wow, that's really cool. So it's a kind of similar process to the creation of kind of oil and those sorts of things, which is, so those are layers of sedimentary rock which have then been compressed. But then within this sedimentary rock, it hits a subduction zone, which is the meeting of two continental plates.
Correct.
And one of them gets pushed underneath the other one to deeper into the crust.
Exactly. That's a good explanation. Yeah, that's it.
Okay. Wow, that's really cool. And gold? Where does gold come from?
Oh, it's a big question. I mean, there's gold. Gold is. We had a paper recently based on gold mines in Egypt with my colleague Tamir Abu Alam, and we're trying to look at the origin of gold. And I don't know how much time you have, but I'll try again in 3 minutes.
Do it.
Well, in that case, we were looking at 550 million year old rocks, right? And it was an interesting system because we were looking at one of the world's largest shear zones called the Nudge Fault System, and we find that the gold mines are located along these major structural breaks in the Earth's crust. And the question that we had was like, where is this gold coming from? Is it coming from the sedimentary rocks? Is it coming from the granites? Where is it coming from? And so we did some modeling, thermodynamic modeling using different rock compositions, granites, metasediments, and also what we call very magnesium-rich ultramafic ophiolite rocks, which are part of oceanic crust. And what we found is that most of the water we can get out during tectonic compression was coming from these ultramafic oceanic rocks. And these fluids contained significant amounts of CO2. And I don't know, when students, sometimes when you blow CO2 into water, you get carbonic acid or Coca-Cola type of fizzy drinks, right? And this type of fluid or this type of carbonic acid is very good at stripping gold out of mafic and ultramafic rocks and carrying the gold up from deep crustal levels into the Earth's surface. But when the fluid gets to the Earth's surface, it reacts with a number of things. It can react with organic material, and then you can change the redox composition of the fluid, and then you can deposit gold in organic rich shales. But you can also change the pH of the fluid as the temperature drops when this fluid reacts with granites in the area. And then you can deposit gold along the margins of granite intrusion or igneous intrusion bodies. And we think that this whole process was happening as part of a single pressure temperature mountain building event. And that, you squeeze the water out, the gold gets dissolved, it gets carried through, and then gets deposited into the shear zones or these major structural breaks in the crust during the time when deformation takes place. So I think that on the early Earth, we might have been seeing a similar process, but a more dynamic process, and on a much hotter early Earth.
The thing I like about geology is it's kind of similar to astronomy in that we talk about these things like they're happening, over a matter of days, when actually it's like tens of millions or hundreds of millions of years. And we have the same issue with astronomy, where it's like, well, a galaxy forms and this does this, supernova go off, but it's actually taking over hundreds of millions of years.
Yes.
And yet we cover it in no time at all. It's fascinating to me, and I think that now I really want to get to the interesting part, the more interesting part, which is what you touched on earlier, was these early organic compounds, and where are they coming from, and sort of what are the conditions on a planet that make it possible for nucleotides or the early building blocks of life to form?
Yeah, Daniel, massive question, I think it's an interesting question. And there's still many open questions that are debated today about the origin of life on our planet and what environmental factors might have driven biological evolution. There are some theories that postulate that organic matter, organic material, was actually introduced to the early Earth by comets and meteorites or carbonaceous meteorites that bombarded the Earth. And we think that the possible place where life may have started could have been at hydrothermal vents on the subsea floor beneath the oceans, where we see hydrothermal fluids and vents developing. There they would have the ingredients for prebiotic molecules to potentially form the building blocks for life. But how we've gone from a geochemical world to a biogeochemical world is still very much debated. We know there's evidence of microbes and microbial activity in seafloor sediments in the Barberton Greenstone Belt as early as 3.5 billion years ago. We have evidence for microbial mats, or what we call stromatolites, that started to form in shallow marine environments by at least 2.9 billion years ago. And then the evolution of complex life emerged 540 to 530 million years ago during a period in Earth history called the Cambrian explosion. I find this interesting because sometimes there are very long periods of time, up to 1 billion years, where biologically there's nothing much going on Earth. And then all of a sudden there's an episodic event or a major evolutionary stage. So there could be a number of geological events that could have triggered life or the formation of life. And for example, the formation of continental land masses giving new ecological niches, or plate tectonic boundaries causing environmental changes. I think the picture that's emerging from research is that from an early stage, Earth and life were interacting hand in hand in a form of evolutionary partnership that formed the world that we live in today. A habitable planet, a precious planet that we need to take care of and protect for future generations.
Absolutely. I mean, that's something which is very topical at the moment with climate change and all the damage we've done to the Earth. And, we're accelerating these processes in a way which is not going to be, it won't be consequential in geological timescales, but it will be consequential to us and to the current sort of state of life.
I wanted to elaborate on that question you asked me about the origin of life. And I thought you might find this interesting because I met a very interesting scientist by the name of Robert Hazen. And he proposed a theory called mineral evolution, where minerals actually evolve like animals on our planet. So The question was, how do we go from no minerals in the universe to up to 4,300 minerals that we know on Earth today? He proposed that the first mineral to form in the universe was most likely microdiamonds that formed as the stars cooled down and exploded in supernova. Then chondritic meteorites formed in the early solar system about 4.56 billion years ago, and they contained about 60 minerals. Then planetesimal differentiation and hydrothermal alteration gave rise to 250 new minerals. Igneous crystallization gave rise to about 500 new minerals. Granite formation gave rise to 1,000 minerals. The beginning of plate tectonics on our planet gave rise, at 3 billion years ago, gave rise to 1,500 minerals. And then the emergence of photosynthetic algal mats on the planet caused the oxygen levels in our atmosphere to rise. And that gave an explosion of new minerals, up to 4,000 new minerals. Other events such as glacial events and also biomineralization and bioweathering, where we form clay minerals, increased the number to more than 4,300 minerals we know today. So it seems that Earth had to go through a series of stages in order to achieve a final complex mineral evolution stage, a planet with a high level of mineral diversity. And in 2015, I wrote a paper with Robert Hazen in astrobiology, where I asked him to address a few questions. For example, why is the Earth the only planet in our solar system that has oceans, continental land masses, and life? And we postulated that at an early stage in the Earth history, microbial life could have co-evolved with Earth from around 4 billion years ago. Microbial life may have been living in subsea floor volcanic environments protected from harsh UV rays on the early Earth, and microbes may have found their way living in volcanic glass, eating nutrients in volcanic glass in a process called bioalteration. The byproduct of this bioalteration process was low temperature clay mineral formation. When you convert a basalt to clay minerals, you can lower the melting temperature of the rock according to our modeling considerations, and as a result, small granites can start to form. So we postulated, and this is just a hypothesis, but that microorganisms could have been responsible for the formation of the earliest microcontinents as early as 4 billion years ago. And this helped the Earth to achieve a high level of mineral evolution, and this would have been very different from and in contrast to the evolution of Mars, where you're unlikely to find complex minerals like a granite or rocks like a granite or a mineral like tanzanite. So I don't know if that answers your question about origin of life.
Yeah, I mean, it's a fascinating concept. Just for our listeners, can you just define, what do you call a mineral? I mean, what's the difference between a mineral and so say an element?
A mineral is basically a structure where we see atoms are arranged in a very organized fashion to form a crystal. It's a non-living mineral, and the atoms are arranged in a very organized fashion in the mineral in a crystalline state. And so normally there are chemical components, like, for example, you could have zirconium and oxide arranged in a crystal structure. And there's basically 6 main groups of rock-forming minerals, and they depend on the arrangement of silica tetrahedra, which is basically silica in coordination with oxygen, that form these prisms that connect to each other in chains or in isolated tetrahedra or in sheets to form sheet silicates like serpentine, for example.
Okay, so we know what a mineral is, and as you mentioned, basically going from the early formation of the Earth to today, there's had to be these various events which have happened in order to create the 4,300 minerals we have today. And without that number of minerals, it becomes very difficult to form life.
Well, what I'm trying to say, I think, is that we think that life and Earth have co-evolved and that life has played a role in making minerals.
Oh, yes. Okay. So all right. So we wouldn't have had 4,300 if we didn't have life.
Correct. Yeah. For example, when these algal mats started to form on the early Earth 2.9, 2.4 billion years ago, they started to use photosynthesis and suck CO2 out of the Earth's atmosphere and produce oxygen. And that oxygen started to increase in the Earth's atmosphere and oxidize the Earth's surface. And as a result, when you take a mineral like an iron-rich mineral, when you oxidize it, just like with a car, for example, it starts to rust. So we start to see rusting of the Earth's surface because we're converting a lot of minerals into iron oxides, into hydrous minerals, and into a whole range of oxide minerals like hematite. So which is an iron oxide mineral. So this oxidation processes gave an explosion of almost 2,000 new minerals because life had a role to play in making those minerals. So there's this interplay between life and Earth, and there was this co-evolution process between the two, these kind of different stages that the Earth and life were involved in.
So you mentioned Mars. This understanding we have of mineral evolution and the early stages of organic life, how can we apply this to other planets? And in recent years, there's been a lot of exoplanet discoveries, and this is a very active, avenue of astronomy. This understanding of the evolution of Earth and how it's the really particular events that have had to happen in order to form life. How can we apply that to these thousands of new planets that we are discovering?
Well, the thing is, we have a statistic of one. We only have the Earth to look at, and Earth is unique in the solar system. So I suppose every planet is different in terms of its evolutionary path. I don't know. I don't really know how other planets have evolved because I haven't looked at their rocks. But I don't know. I don't know if you're asking, for example, how do we apply our knowledge? Well, when we compare Earth and Mars, for example, we know that Earth's atmosphere was very anoxic and had very low levels of oxygen around 3.5 billion years ago, whereas on Mars, the atmosphere was oxidized already by 3.7 billion years ago. So that's why Mars looks red, because it's got a lot of oxidized minerals on its surface. So even between Earth and Mars, if you pull the clock back to 3.6 billion years ago, the atmospheres would have had different histories and different compositions and different redox states. So I think Earth has a unique history. We can learn from it, but I think different planets are going to have different levels of mineral evolution and different levels of sort of different stages of their own accretionary histories or geological histories.
Thank you very much for speaking to us, Eugene. Just to wrap up, what are you excited about on human timescales rather than geological timescales? What's coming in the next 20, 50 years? And, what's really the exciting stuff you're looking forward to?
Well, I mean, there's different aspects. I mean, in geology, I'm excited about early Earth research. I'm excited about training students to do geological mapping in the field and to try and understand how the early Earth worked. There's a new field of research in geology called petrochronology, which is about 10 years old, that I've been involved in. And this uses very high resolution analytical techniques to study tiny chemical compositional changes in minerals and also to date minerals. That gives us better control on understanding the rate of geological processes at high resolution. In astrobiology, I'm excited about developing criteria in searching for life in the solar system, studying ancient rocks and meteorites looking for signs of life. I'm currently working with Dr. Nicola McLaughlin, who studies Martian meteorites, and she studies morphologies and organic material in minerals and meteorites and develops biogenetic criteria and tests for robust evidence for life in extraterrestrial material. And we published a paper on this last year that just a step towards a roadmap in the search for life on Mars and in the solar system. And we're hoping that Mars rovers can give us samples to look for life in hydrothermal environments in the subsurface of Mars. I also have an active collaboration with Dr. Janice Bishop, based at the Carl Sagan Center at the SETI Institute, and also at NASA. We published a paper this year in American Mineralogist Special Issue, Earth Materials for Mars Analog Studies, and we did multiple spectral analysis on different rock powders and crushed rocks and rock slabs from the Barberton Greenstone Belt that's appropriate for Mars rover and remote sensing exploration. We did visible near-infrared spectra and mid-infrared spectral analysis of these crushed rock slabs that are hydrothermally altered. And the spectral data we acquired in this study helps us to expand the reference spectra for remote sensing studies on Mars. The implications of the study are that rocks from early greenstone belts, such as the Barberton Greenstone Belt, they can serve as potential clay-bearing petrological analogs for hydrothermal environments on Mars if you're searching for water on Mars. So this can really help us in the search for water in remote sensing studies of Mars. And also the Mars rover has taken a sample now recently. So we can compare the spectra of the Barberton samples to that of the Mars samples and try to infer the types of clay minerals present on Mars, the types of hydrothermal water environments, and the possible habitable zones for life on Mars.
I imagine everybody in your field is desperate to get hold of those Mars samples. I mean, how are they going to share them out?
Well, firstly, you spoke about the timescales of 20 or 30 years. So the samples are only going to be brought back on the scale of like the next 15 years or something. So the Mars rover is drilling the samples, but we haven't actually got the samples yet. A future Mars mission will collect it. But there are orbital data and there are in situ preliminary data coming from these samples from the rover. So we can maybe, in collaboration with Janice Bishop, we'll try to investigate the types of clay minerals or the types of alteration minerals or whatever types of minerals are in there. So it's quite exciting for me to see that, and we'll see how that pans out in the near future.
Yeah, of course they've got to launch these Mars rocks off Mars with another kind of rover with a rocket attached to it, which then needs to travel all the way back to Earth.
Yeah, but in the meantime, there are orbiters orbiting Mars, and so they doing spectral images looking for clay minerals and water on Mars from orbiters.
It's very, very exciting, and do keep us in touch if you find anything exciting. We'd love to hear from you. And Eugene, thank you very much again for joining us on the Cosmic Savannah. I really enjoyed our conversation, and we'll hopefully chat to you again soon. Do you have any messages for our listeners?
Yeah, a message. Yeah, I mean, if there's any people interested in studying geology is a broad field. There's economic geology, there's petroleum geology, there's exploration geology, there's environmental geology. So if you are interested in outdoors and a career in geology, look it up and see if you're interested in it. There's also planetary geology, which I'm interested in. And so, just follow your dream and your heart in terms of what you want to do.
And we'll obviously put your contact details on the website and people can get in touch with you.
Sure. Daniel, it's been a pleasure chatting to you. Thank you for asking all these big questions. And I hope they satisfy your curiosities and things. So, yeah, thanks.
That's my pleasure. If anything, it's piqued my curiosity to learn even more.
Yeah, that's good.
Great, Eugene. Thank you very much.
Thank you, Daniel. Thank you then.
That was really cool. Thanks, Dan. One might even say it rocked.
Oh, my. This is the kind of thing I normally do. And then you just like pull me apart for making cheesy jokes.
Are you going to give me some stony silence?
Oh. Did you
going.
prepare these? Did you prepare these?
Yes.
Oh my gosh.
Yes, I've been thinking of geology puns all day.
Oh my gosh. Okay. I do apologize for that. Very nice. Well done.
No, but in all seriousness, that was so interesting. I must admit that I'm really quite ignorant when it comes to geology. I was asking my brother, who has a geology degree, some basic questions, just to try and understand more about what Eugene was saying, like, what's the difference between an element and a mineral? And yeah, so I thought that was so interesting, all of the things he had to say. Okay, I have some main topics that I liked the most. First of all, microdiamonds.
Yeah, I know, come on.
Awesome.
Also, just the how diamonds form and, like where they form. And I mean, that there's bands of them down deep in the crust. Like, no wonder people want to dig so deep.
And then like gold that kind of dissolves and then is precipitated out from this substance with like bubbles and things.
We're absolutely crucifying how Eugene explained it, but
yes.
it was, I mean, I really enjoyed it. I mean,
we're not geologists.
Basically, I learned so much. And the other thing was that I hope this isn't how our listeners feel often when we get into the technical details of astronomy, but I felt completely out of my depth. He kept throwing words around and I was like, don't understand that word. Don't understand that word.
Yeah, I mean, I think that we We're sympathizing a bit more with our listeners now, so we have to be better at defining things. No, but so many cool things. Like, I also thought it was really interesting. I just had never thought about the fact that the gas planets are like on the outer parts of the solar system, and that might be because the solar wind blew the lighter elements out further. So, like, you know, all of the gas out further. Of course, that makes sense that the gas is further out and then the rocks are towards the center. Yeah, that's so cool.
Yeah, I know, but and again, it makes complete sense now that you hear it. But
yeah, now that you hear it, you're like, oh, of course that's the reason, but I just had never thought about it before. And yeah, I guess talking about the moon as well, how the moon was formed, you know, something smashed into it and like globbed out a part of the Earth, which then formed together to form the moon. How do we actually know that the moon formed in that way and just wasn't like a captured asteroid or something like that?
I'm not sure exactly, but I think it's something to do with the composition of the moon. So, you know, they've obviously been to the moon 50 years ago now and brought moon rocks back. And I think that by analyzing those rocks, it was clear that there was similarities between Earth's rocks and the moon's rocks, which couldn't be explained, except that if they came from the same source. That's my understanding, at least.
Yeah.
But it may be completely wrong. I'm open to correction.
And maybe also something about the fact that the moon is quite spherical.
Well, I think any object of that mass becomes spherical. So asteroids are odd shapes because they're small. As they grow bigger and the gravity grows, then they get pulled into a sphere. So there's some limit of mass beyond which everything will be a sphere.
That makes sense. Hence all the planets, the stars, everything else is spherical. Yeah. Another awesome thing was that it seems that life played a role, like the formation of life played a role in creating minerals on the Earth.
Yeah, that was very cool. And a lot of them, like most of them. So that this sort of co-evolution and, you know, obviously this was very basic life, but very, very cool. And presumably if you detect these sorts of minerals, and I mean, obviously you would need to get your hands on another rock or an asteroid or something. But if you can detect these minerals, which can only be formed in interaction with life, then that must be some clue too. There's
so much. It just blew my mind. And another thing, Mars oxidized first.
Yeah.
So then it had lots of oxygen in the past.
Yeah, I mean, our oxygen, as far as I know, was formed mostly by life. So Mars had more oxygen when it formed than us, but we used to be a carbon dioxide-rich atmosphere, and then life, plant life, converted that to oxygen, and then over the millions of years, our oxygen concentration rose and rose, and I think that only oxygen-based life like ourselves came later. That's my understanding too. Yeah, we could do this again. We could find someone else and just go all over again.
This conversation could keep going and going.
We'll give you a break. We'll talk about something else and then come back to it.
All right. Okay. Well, I think we've gushed enough about that. Yeah. Thanks, listeners, for tuning in again. And again, good luck to you, Dan, for your awards tonight, and good luck to us, and also good luck to all of the other finalists. There are so many very, very worthy scientists and science communicators who are up for awards tonight, and yeah, it should be a good time. So check out our social medias. By the time this comes out, it will already have happened, but you can scroll back on our Twitter and Facebook and Instagram, and you can see what happened.
And that's it for today. Thanks very much for listening, and we hope you'll join us again for the next episode of The Cosmic Savannah.
You can visit our website, thecosmicsavannah.com, where we'll have the transcript, links, and other stuff related to today's episode.
You can follow us on Twitter, Facebook, and Instagram at Cosmic Savannah, and that's Savannah spelled Savannah.
Special thanks today to Dr Eugene Grosch for speaking with us.
Thanks to our social media manager, Sumari Hatting.
Also to Mark Olnut for music production, Jacob Find for sound editing, Michal Werchek for photography, Carl Jones for astrophotography, and Susie Karras for graphic design.
We gratefully acknowledge support from the South African National Research Foundation, the South African Astronomical Observatory, and the University of Cape Town Astronomy Department.
You can subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts, and we'd really appreciate it if you could rate and review us or recommend us to a friend.
And we'll speak to you next time on The Cosmic Savannah.